In case you're now just joining us, the last video ended with the epoxides, so I figured I'd just throw that summary slide up. So what we're looking at is oxidation reactions of alkenes, and we'll briefly look at alkynes as well. So after the epoxides, we can then move in kind of, I'm not sure why I'm calling it strict oxidation, but these are going to be your full-on oxidation reactions. In each of these, what you'll notice is that we are, or in both of these reactions, we are using a metal. So in that top case, we've got the osmium, which I just covered up the O, or sorry, the S. We've got osmium catalyzing that reaction, and we have manganese catalyzing the reactions down below. Okay. One of the things that's difficult when looking at metal reactions is we aren't 100% positive with a lot of them how the metal is affecting the reaction. We know it's going to contribute to electron withdrawal and all sorts of other fun things, but the exact mechanism is rarely perfectly nailed down. With both of these oxidation reactions, thankfully we have, thankfully it was a bit strong. We do have some type of consistencies between these. In both cases, if you look carefully, we've got the metal and, we got the metal in both cases, and then we have 4 oxygens. So what we're looking at for an overall structure, or some kind of intermediate structure, is the metal with oxygens on the outside. So our characteristics of this is that that metal is extremely positive, okay, because we've got 4 electronegative elements all pulling electron density away. The other thing that makes it difficult is we're shifting into the metals and we have d orbitals, and it just makes a kind of a mess of everything. But it is drawing electron density inwards. So if we just went through and kind of try to draw on all of our lone pairs on these oxygens, what we'd end up finding is that that metal is not particularly happy, and so the oxygens tend to share their electrons inwards. And that usually happens with at least 2 of them. So what we end up with are pi bonds coordinated to the metal ion. Because the metal still wants to change its oxidation state, wants to reduce down, it needs to gain some more electrons. So what ends up happening is it starts to suck electron density from the oxygens. Okay, or 1 oxygen. The reason why that's important is that if that metal ion starts to suck that electron density away, what happens to the oxygen? If the oxygen loses electron density, it starts to become kind of positive. Okay? That polarization of the oxygen is what facilitates the reaction with the alkene. If we go through and kind of evaluate that oxygen, we could also look around at our other oxygens, and in particular the one over here, or the one right below it, we also have a negative. If we then bring the alkene up close to this, and we've got our alkene structure, and if we just pick that one as a nice simple one, remember if we went through and did resonance, the best resonance structure would be to put the electron density on that carbon. We'd have the negative there and the positive there. What ends up happening is that you can now see that we have a matchup of our positives and negatives. That matchup is what's allowing for the attack of the alkene, or the interaction of the alkene with that metal-oxygen complex. And what we end up forming is a pseudo cyclopentane structure, which I've got a nicer image on this shown here. So we've got our metal coordinating its oxygens to what was formerly the alkene structure. This becomes really important because if we look at where our reactions end up, which thankfully we got the summary on the right, the relationship of the oxygens in our products is that they're on the same side of that ring. So we're getting a syn addition of 2 alcohol functional groups. The first step in both of these reactions is the formation of this weird metal complex with our pseudo cyclopentane ring running through that middle. That is then followed up with, in the case of the osmium reaction, with either a couple different reagents. The primary one that you're looking for is what is that? Sodium hydrosulfite, I think. And that is a reducing agent, which will allow for the metal to be reduced, and at the same time, what it's going to leave behind are going to be your oxygens. Okay, so you're going to end up cleaving off your metal species, which will have gained 2 electrons through that oxidation reaction. And I'm not even sure how many oxygens are on there. And we end up with our final product with our alcohols attached. Okay. I know we haven't talked about alcohol nomenclature. That will get covered before the end of the semester, but what we have here is 2 alcohols, so we refer to it as a diol, di being 2, and then the ol ending, as we talked about in lecture, is the alcohol ending. We can take this a step further, and we can refer to this as a cis diol, because the alcohols are on the same side. There are 2 reagents to go through and do this reaction. You'll notice that the osmium reagent does it, and then we can also see permanganate do it. And they're both going to go through a similar transition state where you have that weird cyclopentane dealio. How much you don't really need to know the mechanism except to realize that for that metal complex to coordinate to the alkene, the oxygens have to be on the same side of the ring, because you can't get, if you think back to, as I start to gesture and show you with cyclopropane, you can't get that bond happening across the structure. Let's see, can I think of a way to draw that? If you remember back to when we looked at the addition reaction, so we'll pretend this is 3-dimensional, this one's really far away, this one's really close to you. If we looked at the reaction with the bromine, okay, we had our system set up where the bromine reacted on the same side of that structure, and we had our bromine, in this case, kind of going upwards, okay, to form our bromonium ion. We wouldn't be able to draw it in such a way that we could have the bromine up, and so one of our bonds going up, and then the other bond comes in from the bottom because of the spatial arrangement. The metal complex has a little bit more leeway as far as that arrangement, but it's still not going to be able to go trans across the double bond. It still needs to be cis. Okay. Hopefully that kind of makes sense. So 2 reagents to get you the cis diol. If we went back and looked at epoxides, which is a couple ways back, we could end up with a diol with the epoxides if the nucleophile we used was, say, water in the acid catalyzed reaction, or hydroxide in the base catalyzed reaction. And we would still end up with a diol, but the relationship of those 2 in either mechanism is still going to be trans. So the epoxide formation makes the cis makes a diol, but it's a trans diol in this result. Okay? And that's due to how that reaction works. We're only putting in 1 oxygen at a time, which means we're going to have to get those oxygens as far away from each other as possible. Whereas when we go ahead and look at our metal complexes, we're really putting in both oxygens at the exact same instant, okay, sort of. And that means that we need to get them in there in the easiest fashion possible, and that sterically is going to have to be cis. Okay. Let's just advance slides here. The next issue that we're going to run into, make sure I don't have anything else. Come back here. The next issue we're going to run into with the permanganate is that if you do look kind of closely, yes, osmium tetroxide and permanganate both will generate our cis diols. Okay? However, you take one step to the left, and we use permanganate, and there's no diol. Okay? That's a bit sketchy. What's going on with that? Well, it turns out that permanganate is extremely reactive. Okay? A really, really, really good oxidizing agent. Which means that if we aren't careful with how much permanganate is present or the conditions in which we put it in, it will completely oxidize the structure as much as it possibly can. And that's what ended up happening under these conditions. So when you are trying to decide what the result is of, or where you're trying to get to, we can look at permanganate, and if it's under dilute circumstances, in particular cold dilute circumstances, we should get the diol. If, however, we put it in concentrated and we provide it some heat, what will end up happening is we'll just oxidize the whole crap out of that, and we'll end up with the final state here. Okay? So let's take a look and kind of compare what happened in that structure. So if we go through and identify each of our carbon atoms, so we're going to be focused on the whole left side there now. Go back to our starting material. We have carbon number 1, 2, 3, 4, 5, 6. I'm not numbering for nomenclature's sake. This is numbering to identify where the carbons went so we can find things. Okay, so where do you think these carbons are? That becomes a little bit tricky, so let's kind of piece together where the reaction actually occurred. So when we look at our starting material, what carbons are our reactive carbons? Hopefully you can pick out that our reactive carbons are going to be carbon number 2 and carbon number 6 in this numbering. So if we now look to our product, the reactive carbons in our starting material should still be the most reactive carbons in our product. So if we go back and look at our product, the most reactive carbons are going to be the ones with the carbonyls attached. Okay, so those are either 2 or 6. Okay, and since we haven't fully addressed which one's which yet, but those are going to be our 2 and 6 positions. So now we've got to decide, okay, where is 2, where is 6? Well, what's the difference between 2 and 6? 2 has 3 carbons attached to it, 6 only has 2 carbons attached to it. So 3 versus 2, the 2 carbon, our number 2 carbon that is, should have plus 1 carbon, plus 1 carbon, I keep doing that plus minus, let's try that again, plus 1 more carbon over our carbon number 6. Okay? And you'll notice I'm not just saying 3 and 2, because if we go through and look at our products, no carbon has 3 carbons attached to it. Okay? Taking a step further, our alkene isn't even there, which is why we have to be a little bit careful with that. So what we're looking for is where the differences between those two atoms are, and then trying to space it out and figure out what's happening from there. So carbon number 2 has an extra carbon bond. So if we go through and take a look at our purple circled carbons in our product, the bottom carbon only has 1 carbon attached to it, and our top carbon has 2 carbons attached to it. So our top carbon has an extra carbon. Guess which carbon our top carbon is? That's our number 2. That then says our numbering is going to go around in this fashion. So why go to all that trouble? Well, once we know where our atoms are, we can start to do something about predicting the chemistry of the reaction, or predicting what happened. If we don't know anything about anything, we're just shooting in the dark. So at this point, we now have something to kind of work on and try and figure out what happened. So if we now, again, go back and forth between these, what happened at carbon number 2? Well, I had originally a double bond to a carbon, and it's now a double bond to an oxygen. Oh, well, I increased the electronegative bonds. I made more oxygen bonds. I did an oxidation. What happened to carbon number 6? Well, I got rid of 2 carbon bonds and a hydrogen, believe it or not. Whoops, that's an eraser. There is a hydrogen out there. I got rid of that hydrogen, and I also put on oxygen bonds. So again, I did an oxidation reaction. So the net result of this is massive oxidation at both those carbons. And I didn't oxidize any more. So then the question is, well, why did I not oxidize more? And if you think back to when we first looked at our redox reactions, said one of the things that we needed to have was a carbon with hydrogens on which we could remove. If we don't have the hydrogens, we can't remove them to replace them with oxygens. And if you look at carbon 2 and carbon 6, there's no more hydrogens in our product on those carbons. So I can't oxidize those positions anymore. And I can't oxidize the other positions on it, on the carbon structure, because those other positions aren't reactive carbons because they're only bound out to other carbons and hydrogens. There's no polarity associated with them. Okay, so we really don't have any reactive other carbons to do anything with. It's really just focused at those 2 positions. So what did the permanganate do? Well, what ends up happening is we do go through and we form the diol first. Permanganate is such a good oxidizing agent that it will oxidize those alcohols as well. And it goes through a big old fun dealy-bob of a mechanism that if you really wanted to look up, you can talk to me about and we can go through it. I wouldn't stress about it. Okay? What you're going to be responsible for recognizing that is under hot conditions, hot concentrated permanganate conditions, you will fully oxidize your alkene. So you will convert any multiple bond into a bond with oxygen. Okay? If we have just 2 bonds, then it turns into 2 bonds to a single oxygen. And then the next issue comes up with, what if there's a hydrogen attached to that carbon? Well, that's now a reducible position. We can swap that hydrogen out for an oxygen as well. Okay? So I know, that's a bit of a stretch, but let's see what we can do about recognizing the reagent and then just doing it, getting somewhere with our reaction. Okay, so let's take a look at our starting material again. So what we're going to do is identify the chemistry, which is in that alkene. And what I'm going to do with that alkene is I'm going to stretch that double bond. Okay, I'm going to stretch it a lot. Okay, really, really stretched out. Okay, so stretched out, it looks pretty horrible. So what the permanganate's going to do is cleave that. So I've now stretched it so much that it snaps and breaks. So let's just erase it. Okay, but I'm not going to erase it entirely because I still have those electrons there. Okay, and so what our permanganate does is an oxidation. So we'll stretch that bond and put in oxygens. Okay, but oxygen can't have 4 bonds, so I need another oxygen. So there we go. Okay. Now what I want to do is evaluate other chemistries around those carbons. And what I mean by other chemistries is, do we have hydrogens attached to that carbon? So if we go out to, for our top carbon, we go out to a carbon with 3 hydrogens, but the first atom we encounter is carbon. If we go out the other direction, what do we have? Again, a carbon. No reducible hydrogens. So we can't oxidize that carbon anymore, our blue carbon anymore. So it's left as the ketone functional group. If we go through and look at our bottom carbon, if we go out and look at what it has, well, it's got a carbon there. Can't reduce that any further. And then we look out the other direction and we go, well, there's nothing out there. Remember, carbon must have 4 bonds. So if you go back and look at your starting material, we only show 3. That 4th is an implied hydrogen. There is a hydrogen out there. I have a reducible hydrogen. Permanganate under hot concentrated conditions will fully oxidize, so we need to get rid of that hydrogen and replace it with an oxygen. Oxygen needs 2 bonds, so let's just add our hydrogen at the end. Okay, that's it. Yeah, right. Okay, but that's your answer. Okay, and if we compare that back to what I drew over here, they are one and the same. I just drew it out a lot nicer when I had it on the computer as opposed to drawing it by hand. Okay, so let's try another one. Let's actually go back a little bit because I think I got a little more space. Let's do this alkene. Okay, because I've been sticking with this one a lot. So this one should be nice and easy to stretch. So let's go through that stretch process. Whoops, it's a horrible arrow to use because of the resonance. But we're going to stretch that double bond. Super, super stretched out. Okay, it's so stretched out it breaks. Ta-da! And now we drop in our oxygens. By the way, every time you get an answer right, you should say ta-da. It'll help you out. Now that it's cleaved, remember our permanganate, wicked oxidizing ability. We need to evaluate our carbon. We go out, see carbon, can't touch that. Go out the other direction, see nothing. Go back to your starting material. Oh, that's right, there's a hydrogen there, which means OH. Okay? What about the other molecule? So we go out to that carbon, go out, oh, I don't see anything there. So we go back to our starting material, we go out that direction, oh, there's a hydrogen. So I need to put an oxygen there. So we drop down an oxygen. Ta-da, and we can even put on that H. Why not? What about the other direction? Well, we go out the other direction. Oh, shoot, there's nothing there. So go back to your starting material, see what's out there. Starting material, oh, there's another hydrogen. Before adding an oxygen, we have to fully saturate each oxygen. Okay, so, and by saturate, I mean saturate with carbon-oxygen bonds. So I'm not going to add another oxygen in this case. What I'm going to do is look back to this oxygen and realize I haven't saturated that oxygen with carbon bonds yet. So what I'm going to do is remove that hydrogen and add a new bond. That looks absolutely god-awful horrible. And you'd be right, I think it does look pretty horrible. So let's turn it a little bit. We end up with CO2. Okay? So if we've got a whole bunch of hydrogens that are oxidizable, permanganate will cleave all of those off and drop in more oxygen bonds. Okay? Let's attempt one more quick example. Let's do this guy. Okay? Same idea as before. Stretch that double bond like crazy. Okay? Cleave it, drop in your oxygens. I know those look kind of small. Then go back and evaluate what's attached. Carbon, can't do anything. Ooh, what's out there? Oh, that's right, it's a hydrogen, which means I need NOH. We go to the other side. Whoops, should be in blue. Carbon, can't touch it. Oh, nothing, what's out there? It's a hydrogen. OH. Okay? Where you will typically see this type of problem is with a cyclic structure, which is the one that I gave you the nice example of. Okay, so we end up cleaving that structure up open into a linear situation. The examples that we just went through and worked are cases where it wasn't a cyclic alkene, it was actually a linear alkene. And if we look at the pieces, we started with one piece and we ended with two pieces. Okay? So if we have a linear alkene, we'll end up with two pieces at the end of it. If we start with a cyclic alkene, we'll just end up with one piece because we're just busting open the ring. Okay? I am kind of running short on time, so we'll have to push a little bit further ahead. There is another reagent that is a massive oxidizer, just like our permanganate. That reagent, our conclusion, are osmium tetroxide. So if you see OSO4, focus on diol. Okay? It does officially need to be followed by an oxidizing agent, and you might see NMO. You can check your textbook for that as well. But in most cases, if you're seeing OSO4, all they're fishing for is the cis diol. So go to the cis diol and you should be okay. The permanganate, under dilute and cold conditions, you can get the diol. So the last oxidizing agent that we can deal with, so if you want the mechanism, so we just walked through all of this explanation on splitting the double bond, doing all sorts of weird stuff. So stretch it, and then replace any hydrogen attached to that reactive alkene carbon with an OH. Sorry, I didn't realize I had a nice slide for it. The very last reagent is our ozone reagent. It does all sorts of fun chemistry with organic materials. This is why ozone is typically a bad thing, and we don't like breathing ozone in. That's why there's ozone air pollution warnings. There's a lot of ozone in the air, so don't go outside because it'll hurt you. Because it'll go through and it'll take an alkene and split it open. And we got lots of alkene functional groups in our bodies that we want to keep. Okay, so if we take a look at the result of our ozone, if we run under standard oxidative conditions, you'll notice the product that we get is the exact same product as our permanganate, and that's because ozone is an awesome oxidizer. So if we just let ozone do its thing in the presence of water or even peroxide, okay, so peroxide's another strong oxidizer, we'll end up with that fully oxidated molecule. Ozone does have additional chemistry that's a little bit fun. We can slow the oxidation process. So it's still an oxidation reaction because we are converting our alkene, notice the alkene, into carbon-oxygen double bonds. So it is still an oxidation reaction. However, it's not as strict an oxidation reaction because we don't end up removing that reducible hydrogen. Okay, so we're looking at an oxidation reaction that is uber oxidative and not so oxidative. Okay, so usually what you'll hear as terms is ozone followed by reductive conditions or ozone followed by oxidative conditions. If it's oxidative, oxidate the crap out of it. Pull off those hydrogens, throw on oxygens, and be happy. If it's reductive, all you can do is stretch that double bond, drop in your oxygens, and you're done. So the reductive conditions are kind of nice. So what you'll need to look for is kind of key signifiers or secondary reagents. The oxidative conditions, you're looking at peroxide. Your reductive conditions, zinc tends to be a pretty good reductive condition. The other one is this thing known as DMS. If we draw that structure out real quickly, should look kind of familiar, okay, particularly for those of you that remember your solvents well. So that's DMS. What ends up happening is because ozone is such a strong oxidizing agent that if we don't want it to completely oxidize our alkene across, we need to throw something in there that'll get oxidized instead. This structure will do that. DMS will get oxidized to become, everybody know this one? DMSO, dimethyl sulfoxide, as opposed to dimethyl sulfide. Okay? So that is a very common one to see pop up, just because you can convert DMS to DMSO, and everybody goes, "Woo, DMSO." Okay, they aren't really that excited about it. This is one as well that I really don't want to go through a mechanism on. If you would like the mechanism, if you download the slides and go to this slide, there's a bunch of text. Delete that text or move the text out of the way, and you should see this mechanism pop up behind it. Up to you if you want to use it. It's there. You can look at it, pause the video if you like, draw it all out. It's just not going to be necessary for you to really know that mechanism. What you need to know is that ozone will oxidize. Stick with that and you should be good to run. Okay? So your conclusion in this, when you're dealing with ozone or when you see it under reductive conditions, stretch that alkene just like we did with the permanganate, and turn it or erase the middle of it and drop in your oxygens. Okay? If it's under oxidative conditions, either on its own or with peroxide, you're going to do the same thing that you did with the reductive conditions, except now convert any hydrogens into OHs. And that will be your reductive condition for it. I've got a bunch of practice here. I'm not going to go through it because we're definitely out of time here. So if you got questions, please feel free to talk to me on Fridays. I'll be hanging out. There's an announcement on Canvas explaining that. So here's some practice. I'll let you decide if you want to pause and work some problems. And just for the heck of it, here's even more practice. Okay. This one I actually stole from the internet. This one I think I made on my own. Okay. So feel free to pause the video and start working through those. What you're going to need for this practice is finding the reagents. Some of these will be multiple steps, some of them you'll be able to do in single steps. Okay, so it's just a lot of practice shuttling different reagents in and kind of seeing what happens. Okay, if you got questions, send me an email. Glad to help you out.